13:47 hours. 18 Japanese Zeros were diving on our formation from 22,000 feet. I was flying a P-38 Lightning with a piece of piano wire that cost 12 cents. My name was Lieutenant Colonel Charles MacDonald, and according to every performance manual in existence, my aircraft was about to be shot down. The Lockheed P-38 Lightning had a documented turn radius 23% wider than the Mitsubishi A6M0. In a turning fight, physics favored the enemy, but someone had twisted a piece of music wire around my aileron control cables. And physics was about to discover that engineering could rewrite the rules of aerial combat. Archive records from December 1942 show that P-38 Lightning squadrons in the Pacific were suffering catastrophic losses. The 475th Fighter Group reported a kill-to-loss ratio of 1.3 to 1 against Japanese fighters. For every 4 P-38 shot down, American pilots destroyed 5 Zeros. That mathematics meant defeat. The United States was producing aircraft faster than Japan, but not fast enough to sustain those casualty rates. Something had to change, or American air power in the Pacific would collapse within 6 months. Can you picture the tactical situation? Japanese Zero fighters controlled Pacific skies through superior maneuverability. The A6M could turn any American fighter at altitudes below 20,000 feet. American pilots had been trained to use altitude and speed advantages, but Pacific combat occurred at medium altitudes where Japanese aircraft excelled. Standard doctrine called for hit and run tactics, diving attacks without dogfighting. But combat rarely follows doctrine perfectly. I was assigned to the 475th Fighter Group at Dobodura airfield in New Guinea. The airfield itself was carved from jungle swampland using bulldozers and coral fill. 2 runways, each 4,800 feet long, built in 37 days by engineer battalions working 20-horse shifts. The climate was brutal, 105 degrees Fahrenheit, with 95% humidity. Rainfall averaging 180 inches annually. Aircraft maintenance occurred in open-air hangars made from salvaged aircraft aluminum and canvas tarps. Our mission was simple: destroy Japanese air power before they destroyed us. The reality was more complex. Every mission resulted in losses. Every engagement favored enemy aircraft. Japanese pilots averaged over 1,500 combat hours, many with experience dating back to the China campaign in 1937. American pilots averaged 200 hours, most of which consisted of stateside training rather than combat experience. Experience matters in aerial combat, but it matters less than aircraft performance when the performance gap is wide enough. The problem was aileron control at high speeds. The P-38 Lightning used a unique twin-boom design with the cockpit mounted between 2 engines. This configuration created exceptional stability and firepower concentration, but it also generated severe control forces during high-speed maneuvers. Aileron cables ran from the cockpit through the center nacelle, down into the left boom, across to the right boom, then back up to the aileron surfaces. Total cable length exceeded 48 feet per CD. Above 400 miles per H-hour. The ailerons became almost immovable. Physics was working against the pilot. Air pressure on the control surfaces increased with the square of airspeed. At 300 miles per hour, aileron force required 15 pounds of stick pressure. At 400 miles per hour, the same deflection required 45 pounds. At 450 miles per hour, some pilots could not move the controls at all. Pilots needed both hands and maximum physical strength to roll the aircraft. Combat maneuvering sessions lasting more than 10 minutes left pilots exhausted. In combat, that limitation was fatal. Japanese pilots recognized the P-38's high-speed control problems and deliberately forced engagements into speed ranges where American aircraft could not maneuver effectively. Do you understand what this meant tactically? Japanese Zeros could turn P-38s at any speed, but P-38s could dive zeros due to superior structural strength and heavier wing loading. American pilots were supposed to dive away from trouble, extend distance, then climb back to altitude for another attack. That worked in theory and practice. P-38 pilots could not pull out of high-speed dives quickly enough. The aileron forces were too high. Pilot Lieutenant William Clark documented this problem in his combat report from the 18th of November, 1942. Clark dove away from 6 zeros at 18,000 feet, reached 480 miles per hour in the dive, then found himself unable to pull out of the descent. He required both hands on the control stick and maximum physical effort to achieve a gradual recovery that carried him down to 3,000 feet altitude before he regained control. The zeros followed him down and nearly shot him down during the extended recovery. Many aircraft dove straight into the ocean because their pilots lacked the physical strength to recover. Squadron records show that approximately 15% of P-38 combat losses between October and December 1942 were attributed to high-speed control problems. Rather than enemy action, pilots were literally flying aircraft that they could not control effectively at combat speeds. Reports from squadron commanders reached higher headquarters by November 1942. The P-38 Lightning was failing in Pacific combat, not due to mechanical unreliability or structural weakness, but due to control system limitations that prevented pilots from using the aircraft's advantages effectively. Lieutenant Colonel Gerald Johnson, commanding officer of the 9th Fighter Squadron, submitted a detailed report on the 28th of November documenting the tactical problem. His analysis included specific examples. During a mission over Wewake Airfield on the 25th of November, 4 P-38s encountered 8 zeros at 15,000 feet. The temperature was 89 degrees Fahrenheit, humidity 92%, with scattered cloud cover providing limited concealment opportunities. Standard American tactics called for diving away to build speed, then using superior power to weight ratio to climb above the enemy formation. 3 P-38s attempted this maneuver. 2 pilots discovered they could not pull out of their dives quickly enough due to control force limitations. 1 aircraft dove into the ocean at approximately 520 miles per hour. The pilot, Second Lieutenant Frank Morrison, was recovered by rescue boats, but died from impact injuries. The second pilot managed to recover at 500 feet altitude, but was immediately attacked by pursuing zeros and shot down. Only 1 P-38 successfully executed the prescribed tactical maneuver. Johnson's report concluded that the aircraft's control system made standard fighter tactics impossible to execute safely. Technical representatives from Lockheed Corporation were ordered to New Guinea to investigate the problem and develop solutions. The corporate response was predictably bureaucratic: extensive testing, detailed analysis, formal design review, production planning, implementation timeline extending 6 months into the future. American pilots did not have 6 months to wait for solutions. The solution came from an unexpected source. Staff Sergeant Anthony Riske was a control systems specialist assigned to the 475th Fighter Group Maintenance Section. His civilian job had been piano tuner in Detroit, working primarily on Steinway and Baldwin concert instruments. He had learned to adjust cable tensions measured in pounds per square inch to eliminate friction points that affected key response, to diagnose mechanical problems through sound and feel. When he examined P-38 aileron controls, he recognized the problem immediately. The control cables were routed through too many pulleys, creating excessive friction and mechanical disadvantage. Each pulley introduced approximately 8% friction loss. 6 pulleys meant the pilot was only receiving 60% of his control input as actual aileron movement. The remaining 40% was absorbed by mechanical resistance. In high-speed flight, when control forces increased exponentially, that friction became insurmountable. Riske had seen similar problems in piano action mechanisms, where hammers failed to strike strings with sufficient force due to mechanical friction in the key action. Witnesses recalled Riske's first modification attempt on the 15th of December, 1942. He removed 6 feet of piano wire from a wrecked Japanese aircraft. Specifically, a Kawasaki -61 fighter that had crashed during a strafing attack on the airfield 3 days earlier. The wire came from the aircraft's control cable system. Riske examined it under a magnifying glass, tested its tensile strength. Using improvised equipment, determined that the metallurgy was actually superior to standard American aircraft cable. He spliced it into the P-38 aileron control cables, using a technique he had learned from piano manufacturers in Detroit. The process required precise measurement of cable tension, elimination of any slack that would create dead zones in control response, and careful routing to avoid sharp bends that would cause premature failure. The wire was 0.032 inches in diameter. High tensile steel designed to withstand thousands of pounds of tension without stretching. Riske created junction points using silver solder and aircraft grade wire nuts, techniques that violated standard maintenance procedures, but achieved results that met combat requirements. He installed it as a bypass cable that transferred aileron input directly to the control surfaces, eliminating 3 pulleys and reducing friction by an estimated 40%. The modification took 8 hours of precise work using tools improvised from maintenance shop equipment and salvaged aircraft parts. The test flight lasted 18 minutes. Lieutenant Robert Smith flew the modified P-38 through a series of high-speed maneuvers designed to stress the control system beyond normal operational limits. The aircraft was P-38F serial number 42 to 12647. Manufactured at Lockheed's Burbank facility in September 1942. Smith took off from Dobodura's main runway at 0847 hours local time, climbed to 15,000 feet, then began the test sequence. At 425 miles per h, Smith could roll the aircraft using only one hand. The previous week, the same maneuver had required both hands and maximum physical effort. At 450 miles per h, our aileron response remained crisp and immediate. Smith pushed the aircraft to 480 miles per h in a shallow dive, then attempted a high G recovery that would have been impossible with standard control cable routing. The aircraft responded instantly. Maximum roll rate increased from 45 degrees per second to 78 degrees per second. Turn radius at high speed decreased by approximately 15%. Most importantly, pilot fatigue during extended combat maneuvering was reduced dramatically. Smith landed after the test flight and immediately requested permission to take the modified aircraft into combat. The 12-cent piece of piano wire had transformed the P-38's handling characteristics completely. But one test flight meant nothing. Combat would determine whether the modification actually worked. The combat test came 3 days later. Smith's flight of 4 P-38 encountered 12 Japanese Zeros at 18,000 feet altitude, 70 miles northeast of Dobodura. Standard American tactics called for diving away from enemy fighters, extending range, maintaining speed and altitude advantages. Smith tried something different. When the Zeros turned to pursue, he turned with them. After, action reports describe what happened next in minute detail. Smith's P-38 out turned the lead Zero in a sustained right-hand turn. The engagement began at 18,000 feet altitude with both aircraft at approximately 300 miles per h. The Japanese pilot, Lieutenant Commander Hiroshi Yamamoto, according to captured documents, initiated the turn expecting the American aircraft to dive away as P-38s had done consistently for 6 months. Instead, Smith tightened his turn radius and began gaining angular advantage. Yamamoto pulled his Zero into a maximum performance turn, bleeding airspeed from 300 miles per hour to 180 miles per hour to maximize turning rate. Smith maintained 250 miles per hour throughout the engagement, using the piano wire modification to achieve turn performance that matched the Zero despite higher airspeed. The engagement lasted 90 seconds. Smith achieved firing position and opened fire from 400 yards range with a converged pattern from 4.50 caliber machine guns and 120 mm cannon. The burst lasted 3 seconds. 27 rounds struck the Zero's engine compartment and cockpit area. The Japanese aircraft exploded in mid-air. The remaining 11 Japanese fighters broke off immediately, not retreating to reposition for another attack, but fleeing the engagement completely. Radio intercepts later revealed that the surviving pilots reported encountering a new type, American fighter, with superior turning capability. Here is what the Japanese pilots observed: an American P-38 Lightning executing turning maneuvers that contradicted every intelligence report they had received about American fighter capabilities. Japanese tactical doctrine was based on the assumption that P-38s could not dogfight effectively. When that assumption proved incorrect, their entire tactical framework collapsed. Fear is a weapon as powerful as cannons, and uncertainty multiplies its effectiveness exponentially. Word of the modification spread through American fighter squadrons within days. Every P-38 pilot wanted the piano wire installation. Maintenance crews learned to splice steel cable using techniques that Sergeant Riske demonstrated personally. By January 1943, approximately 200 P-38 Lightning fighters in the Pacific Theater had been modified with piano wire aileron bypasses. The cost per aircraft was less than $15. The tactical impact was immeasurable, but success created new problems. Japanese intelligence gathered reports of American fighters exhibiting unexpected performance characteristics through multiple sources. Surviving pilots provided detailed after-action reports describing P-38 aircraft executing maneuvers that contradicted established performance data. Ground observers reported American fighters out, turning Zeros in sustained engagements. Radio intercepts indicated American pilots were deliberately seeking turning fights rather than avoiding them. Their response was predictable and professional. If American aircraft capabilities had improved, Japanese tactics needed to evolve accordingly. Flight training schools at Kasumagura and Tsuchiura began teaching Zero pilots new defensive maneuvers specifically designed to counter improved P-38 performance. Japanese intelligence officers interrogated captured American aircrew extensively about aircraft modifications and performance improvements. Zero pilots began avoiding turning engagements with P-38s, instead relying on superior climb rate and service ceiling advantages. The technical solution had forced tactical adaptation across the entire Japanese naval air arm. This demonstrates the fundamental principle of technological warfare. Every advantage is temporary. Innovation creates tactical superiority until the enemy develops counter-innovations. The side that adapts fastest maintains operational advantage, but adaptation requires recognition of change, analysis of new threats, development of counter-measures, and implementation across entire operational theaters. That process takes time, and time is a resource that can be exploited. Japanese naval aviation faced a systematic problem. Their tactical doctrine had been optimized for fighting early war American fighters with known performance limitations. The entire training system at Kasumagura Naval Air Station emphasized exploiting P-38 weaknesses in turning combat. When those weaknesses suddenly disappeared, Japanese pilots found themselves using tactics that were no longer effective. Retraining experienced combat pilots required months of intensive instruction. Japan did not have months to spare. American industrial capacity was delivering new aircraft faster than Japan could train pilots to counter them. Meanwhile, American pilots were gaining experience with improved aircraft performance developing new tactical procedures that maximized their advantages. The piano wire modification had created a cascading effect that extended far beyond individual dogfights. The psychological impact extended beyond immediate tactical effects. Japanese pilots had been trained to expect certain performance characteristics from American aircraft. When those characteristics changed without warning, pilot confidence suffered. Combat effectiveness depends on predictable variables. When variables change unexpectedly, decision-making becomes hesitant. Hesitation in aerial combat is usually fatal. The piano wire modification didn't just improve P-38 performance. It undermined Japanese pilot confidence throughout the Pacific theater. Combat statistics from February 1943 reveal the broader impact. The 475th Fighter Group's kill-to-loss ratio against Japanese fighters improved to 4.2 to 1. Other P-38 squadrons reported similar improvements. American pilots were winning turning engagements that they had been losing consistently for 6 months. Japanese air units were avoiding combat when they detected P-38 formations, reducing their operational effectiveness, even when American fighters were not shooting them down. The modification influenced aircraft design philosophy permanently. Lockheed Corporation incorporated Sergeant Riske's cable routing improvements into P-38L production models, starting in April 1943. But the corporate response was slower and more conservative than the field modification. Lockheed engineers spent 6 weeks analyzing the piano wire installation, conducted extensive testing at their Burbank facility, and ultimately approved a modified version using standard aircraft cable. The production modification achieved approximately 60% of the improvement that Riske's installation provided. However, Lockheed recognized a larger principle. Control system responsiveness could be as important as engine power or structural strength. Future fighter designs would prioritize pilot control authority at high speeds, ensuring that aircraft performance could be utilized fully under combat conditions. The P-80 Shooting Street AR, America's first operational jet fighter, featured control systems designed specifically to avoid the high-speed control problems that had plagued the P-38. Flight testing revealed that proper control system design could eliminate physical force requirements that exhausted pilots during extended combat. This principle influenced every American fighter aircraft developed after 1943. Can you see the broader implications? One maintenance sergeant with a 12-cent piece of piano wire had identified a fundamental flaw in American fighter design philosophy. Military aircraft were being optimized for stability and ease of production, rather than combat maneuverability. The modification proved that small changes in control system design could create disproportionate improvements in combat effectiveness. That lesson influenced American aircraft design for the remainder of the war. The technical success also demonstrated the importance of field modifications in wartime aircraft development. Official engineering channels were too slow to address urgent operational problems. Combat squadrons needed immediate solutions, not solutions that would be available after 6 months of design review and testing. Sergeant Riske's modification bypassed formal approval processes and proved itself in combat before anyone could object to its implementation. Japanese forces attempted to develop countermeasures, but the fundamental aircraft performance gap had shifted in America's favor. Intelligence reports from captured Japanese documents reveal the scope of their analytical effort. The Technical Research Institute in Tokyo assigned a team of 12 engineers to study American fighter performance improvements. They conducted wind tunnel tests on captured P-38 components, analyzed wreckage from crashed American aircraft, and interviewed Japanese pilots extensively about observed changes in American fighter capabilities. Their conclusion, documented in a report dated May 15, 1943, was that American aircraft industry had developed new supercharger systems that increased power output at medium altitudes. This analysis was completely incorrect. but it demonstrated that Japanese engineers were looking for complex technological solutions to explain the performance improvements they observed in combat. Zero fighters retained superiority in climb rate and sustained turning ability, but P-38s now matched them in instantaneous turn rate and exceeded them in diving speed and level flight speed. The combat envelope, where Japanese fighters held advantages, had been reduced to specific altitude and speed combinations that occurred infrequently in actual aerial combat. American pilots could choose when to engage and when to disengage, dictating the terms of aerial combat. This represented a fundamental shift in tactical initiative that extended beyond individual dogfights to influence entire air campaigns. By June 1943, reports indicate that Japanese air units in the Southwest Pacific were suffering unsustainable losses against modified P-38 squadrons. The Japanese response was strategic rather than tactical. They withdrew experienced pilot units to home islands for defense preparations, replacing them with less experienced pilots who were ordered to avoid combat with American fighters unless absolutely necessary. This decision represented a fundamental shift in Japanese air strategy from offensive operations to defensive conservation of resources. The Japanese Combined Fleet Air Force had lost approximately 60% of its experienced pilots between January and June 1943, including the squadron leaders essential for training new pilots. The piano wire modification had contributed to a fundamental shift in Pacific air power balance by accelerating the attrition of Japan's most valuable human resources. Japanese training facilities could replace aircraft more easily than they could replace experienced pilots. The strategic impact extended far beyond individual aerial engagements to influence the entire timeline of Pacific campaign operations. American air superiority was achieved months earlier than originally planned, enabling accelerated ground operations and shortened campaign schedules throughout the island. Hopping offensive, the modification remained classified until after the war ended. American intelligence officers recognized that the piano wire installation represented a significant tactical advantage that needed protection from enemy discovery. Standard operating procedures required that any aircraft with the modification that was forced down in enemy territory should be destroyed completely to prevent technical intelligence gathering. Pilots were briefed specifically about the modification's classified status and instructed to avoid discussing it in radio communications that might be monitored by Japanese intelligence services. Security measures included code names for the modification, improved ailerons in written reports, Package X in verbal communications. Japanese intelligence never determined exactly why P-38 performance had improved so dramatically. Their technical analysis focused on possible engine modifications, new propeller designs, or aerodynamic changes to the airframe. The possibility that a simple cable routing change could transform aircraft performance characteristics was considered but dismissed as too minor to create such significant tactical effects. Japanese engineers captured several P-38 aircraft during 1943. And conducted detailed examinations looking for performance improvements. They found evidence of maintenance modifications, but did not recognize the significance of altered cable routing. The piano wire itself was so inconspicuous that Japanese analysts assumed it was standard equipment. They attributed the change to new engine installations, improved pilot training, or different tactical doctrines. The actual explanation that a piece of piano wire had eliminated control system friction was too simple to be credible to enemy analysts expecting complex technological solutions. Archive documents reveal that Sergeant Riske received no formal recognition for his innovation during the war. He remained at Dobodura airfield until March 1944, then transferred to the Philippines for B-25 bomber maintenance duties. After the war, he returned to Detroit and resumed piano tuning. He worked for 37 years after the war before retiring in 1981. He never discussed his wartime service publicly, partly due to security classifications. He died in 1981 without ever discussing his wartime contribution to aerial warfare. Lieutenant Robert Smith flew the first combat test of the piano wire modification and achieved the first confirmed kill using the improved aircraft. He survived 127 combat missions and was credited with 11 aerial victories. Smith's combat record included engagements over Rabaul, Wewak, Hollandia, and Biak. During the New Guinea campaign, his most significant victory occurred on the 18th of April, 1943, when he shot down 3 Zeros in a single engagement over Simpson Harbor. That mission lasted 4 hours and 23 minutes, during which Smith's flight encountered 47 Japanese aircraft in multiple waves. Without the piano wire modification, Smith later stated, he would not have survived the extended combat maneuvering required during that engagement. After the war, he became a test pilot for North American aviation and contributed to the development of jet fighter control systems. Smith credited the piano wire modification with saving his life on at least 6 occasions when high-speed maneuvering was required to evade enemy fighters. He flew the F-86 Sabre during the Korean War and achieved 2 additional aerial victories against MiG-15 fighters. Smith retired from the Air Force in 1965 as a full colonel, having flown over 200 different aircraft types during his career. The broader impact of the modification extended beyond World War II. American fighter aircraft developed during the 1950s incorporated control system design principles that originated with Sergeant Riske's piano wire installation. The F-86 Sabre featured hydraulically boosted controls that eliminated pilot force requirements during high-speed maneuvering. The F-100 Super Sabre incorporated full-time hydraulic flight controls that maintained consistent control response regardless of airspeed. The F-104 Starfighter used electrical flight controls that translated pilot inputs into electronic signals, completely eliminating mechanical control cable systems. Each of these designs addressed the same fundamental problem that the piano wire modification had solved temporarily, ensuring that pilots could control their aircraft effectively under all flight conditions. American aerospace engineers recognized that control system responsiveness was not just a matter of pilot comfort, but a critical factor in combat effectiveness. Modern fighter aircraft feature control systems that are designed specifically to avoid the control force problems that plagued early jet fighters. The F-16 Fighting Falcon, developed 30 years after the piano wire modification, uses fly-by-wire controls that make the aircraft more maneuverable than any human pilot could control using manual systems. This technological evolution traces its origins directly to lessons learned from field modifications like Sergeant Riske's piano wire installation. Military aviation had learned that pilot-aircraft interface design could be as important as aerodynamic performance in determining combat effectiveness. But the most significant legacy was philosophical, rather than technical. Military aviation recognized that operational problems required immediate field solutions rather than lengthy engineering studies. Combat units were authorized to modify aircraft systems when operational necessity demanded it, subject to safety verification but not bureaucratic approval processes. Innovation became decentralized, moving from corporate engineering departments to operational squadrons where problems were encountered daily. This principle influenced Cold War aircraft development and continues to shape military aviation today. Modern fighter aircraft feature modular systems that can be modified quickly to address emerging threats. Software-defined control systems allow flight characteristics to be altered without hardware changes. The tradition of field modification that began with piano wire on P-38 Lightning ailerons remains fundamental to military aviation's approach to technological adaptation. Did a 12-cent piece of piano wire change the outcome of the Pacific War? Historians continue to debate the strategic significance of individual technical improvements, but the modification demonstrates that innovation often comes from unexpected sources, that small changes can produce disproportionate effects, And that field experience frequently identifies solutions that formal engineering processes miss. One maintenance sergeant with practical knowledge proved that sometimes the simplest solutions are the most effective. What would you have done when official procedures were too slow to save lives? Would you have waited for approved modifications, or would you have improvised solutions using available materials? Sometimes the difference between victory and defeat comes down to someone willing to try a 12-cent fix that everyone else dismissed as too simple to work. If these forgotten innovations that shaped modern warfare mattered to you, hit that notification bell and help us preserve the technical history that most people never hear about. These stories disappear when the people who lived them are gone, but the lessons they contain remain as relevant as ever.